So hello and welcome everyone. My name is Michael Wessely. I'm a postdoc currently at the HCI Engineering Group at MIT CSAIL. And today's talk will about fabrication of large-scale user interfaces. This work has been done with my colleagues from MIT CSAIL and my collaborators from University of Bath and University of Bristol. All right, so our today's question would be, how can we make large objects interactive? This is actually a quite challenging task, because if you think about with what kind of ways you would nowadays fabricate something that's interactive, you would most likely use some kind of a fabrication device. This might be something like a 3D printer or a laser cutter, maybe printing electronics with a screen printing frame or an inkjet printer. But what have all of these fabrication devices in common? And this is that they have always a limited printer volume. So if you use a 3D printer, it's really hard to print something that is larger than the 3D printer. The same is of course true also for like a screen printing frame or for an inkjet printer. So I want to illustrate this directly with an example. So you see here how we use an airbrush system to spray conductive inks and to spray a continuous touch slider on a wall. And here we are not limited by some kind of printer's volume or so. We can pretty much spray it as large as we want as long as we can reach it. So, and once these interactive elements are sprayed, you can also add some custom designs, as in this case, the design of a spray can. And here you see this in an application example. So we've sprayed here an electroluminescent touch display. And once the user touches this display, he or she can turn on the lamp. And these touch sliders that you just have seen in the previous example can now be used to also adjust the brightness of this lamp or to set a specific color. And by this you can control the light environment in your room or in your office. So also other researchers were interested into this question, how we can make large-scale user interfaces. And some work has been done on interactive walls. So for example, Büchle and colleagues and Zhang and colleagues published papers on interactive walls. Zhang also in 2017 published a paper Electric, which is about sensing continuous touch by spraying conductive material on curved objects. So these projects also have in common that they usually use something like one material, so like one conductive material. It's a single material fabrication process. So and this is not sufficient if you want to spray like more advanced user interface elements, like for example electroluminescent displays. So and this is the contribution of this work. So we contribute here a single and a multi-layer fabrication approach. The single layer fabrication approach enables to spray sensors, for example touch sensors, and the multi-layer fabrication approach allows to also spray electroluminescent touch displays. And this is in particular challenging and advanced for makers, as you have to carefully align each one of the layers to produce a functional interactive element. So, and since this can be a challenge, we also developed a digital design toolkit and a full end-to-end fabrication pipeline that supports the maker with automatically generated stencils. So at first, what kind of materials do we need here? So our fabrication device is an airbrush system, which consists of a compressor that produces the compressed air and an airbrush gun that has a little tank in which you can fill in the inks. And by pressing it, you can spray these inks on the surface of objects. Then these inks are functional inks. They have specific functions. Some of them are conductive, but there also are phosphor inks that can light up when put into an electric field. But of course, most importantly, they are safety tools, because if you spray something, you create fog particles in the air, which you really don't want to breathe in. So you have to use a respirator, safety gloves, and safety glasses. Wonderful. So let's first focus on how the single layer fabrication actually looks like and how we can fabricate sensors with this approach. So here you can see how this can look like. So we spray here on a soft and curved leather sofa. We have here a set of projected stencils, and we use the airbrush to spray a transparent conductive ink directly on the surface of the sofa. So we follow here the projected stencil, and once we are all finished with this, we have to let it dry. And after it is dried, these traces are fully conductive, as you can see it here in this example, and they can be used for sensing user input. So what kind of materials do we use for the single layer fabrication approach? We have two conductive inks here. On the left hand side you see a copper ink. This is a highly conductive material that is not transparent but can be used for high current applications and for connecting different elements with a controller unit. And on the right hand side you see a clear conductive material. This is a conductive polymer called P.PSS, which is very useful for making your user interfaces invisible, or for electroluminescent displays if you want to actually see light coming out of your elements. And the layers that you have to spray here can be, for example, touch and proximity layers, here illustrated as a circle, but they can actually have any kind of shape that you want. Then continuous touch sliders out of multi-touch segments. And of course, all these components have to be connected somehow to a controller unit, like an Arduino, for example. So you can also spray wires with this approach and wire then the interactive elements to a controller connector. Good, so how does the multi-layer fabrication looks like, and how can we make electroluminescent touch displays with this approach? So here you can see how spraying a display looks like. We first start with one layer of conductive copper that you spray in a specific shape, here supported with some fabricated stencils. Then you add a dielectric layer, a light-emitting phosphor layer. Then you have to spray a copper frame around the entire display to make sure that you have an even distribution of electric energy on the display, to make sure that it's not brighter at some locations and darker, dimmer in other locations. And finally, you top it off with a layer of clear conductive material, such that you can also see how the phosphor glows. And in a practical example, this looks like this here. So we sprayed here an electroluminescent displays in the shape of a light bulb. And when a user comes to this light bulb and touches it, you can use it as a switch and then turn on the lamp. So just briefly, an electroluminescent touch displays consists out of 4 different materials. And most important is the phosphor layer here as a yellow layer. In the middle of the display, this is the light emitting layer, and this phosphor layer starts to emit light when it is inside of an electric field. To generate this electric field, we have to sandwich this phosphor layer between 2 electrodes, and we use here a copper conductive layer on the bottom and a clear conductive layer on top, such that we can also see the phosphor when it is lighting up. And to make sure that there is no shortcut between them, we have to insulate the bottom electrode and the top electrode from each other, which we do with a dielectric layer. And then, as you can see it here in this multi-layer stencil figure, you have then to stack all these layers on top of each other until you then have a functional electroluminescent display. All right, so now we have all our basic techniques and our basic functionalities at hand. So how does this full end-to-end fabrication pipeline exactly looks like? So, and this is in 3 steps. So we start on the left-hand side with the design toolkit. So we can create a digital model of our object that we want to make interactive. And then we can add functionality and designs to it. Once this is done, we can export these designs in the shape of a stencil. So this can be fabricated stencils and projected stencils. And once we have these stencils, we can then just spray all our functional inks on the surface of the object that we want to make interactive. So let's first start with the design toolkit. So it all starts with creating a digital model of the object that you want to make interactive. In our case here, in our example, we have a wall, so this is quite simple. You just have to measure the dimensions of the wall and then just create the object yourself in Blender. But you can also use a mobile app for 3D geometry capturing, and then just walk around with your mobile phone around the object and then let this app create a 3D model for you. Once you have this, we implemented a set of tools that enable makers to add functionality to these digital designs. So at this example here, we want to add a slider to this design. So we select a slider tool, and then we just draw a straight line on top of the design element that we want to make interactive with a continuous touch slider. So once this is integrated, of course, we have to connect all these touch segments to a controller unit. So we select the wire tool and then just draw the wires from each one of the segments down to the controller connector. And of course, we wanted to make this interface as easy to handle as possible. So we designed everything in a layer-wise approach. So we have an electronics layer and we have a design layer, and you can also overlap these 2 layers to see if everything is aligned properly, if the interactive elements really correspond also to your designs. And you can change each one of these layers until the design really fits to what you wanted to fabricate. All right, now that the design is ready, let's focus on exporting stencils. So here we use two different types of stencils. We have fabricated stencils and projected stencils. Let's first start with the fabricated stencils. So fabricated stencils are laser cut out stencils out of a material like cardboard, for example, or paper. And they offer a really high precision, and it's quite easy to spray because you just have to apply them on the surface of the object and start spraying. On the other hand, depending on what kind of material you use, it might be somehow hard to wrap these stencils around a more complex geometry. For example, something doubly curved like a ball. In our user interface, this looks just like that you press the export button, then our system creates a vector graphic of your design, which you then can load into a laser cutter and automatically let it laser cut out. So on the other hand, we support projected stencils, and these projected stencils are particularly useful in situations where you have a more complex geometry, where you have objects that are much larger, and they also bring the additional feature that you don't have to fabricate any kind of stencil, because you just have to project it on the surface of the object. What Blender here needs is just the location and the orientation of the projector, and then can start directly. So this comes, of course, also with a disadvantage, and this is that you now just have a guideline where to spray, but you still have to spray this freehand. So it comes usually with a slightly lower precision. However, you can also combine the advantages of both stencil types. And this is that you can use the projected stencil as a guideline where to put your fabricated stencil. So in this way, you have the full control over your entire design, and you can then fabricate parts of the design as fabricated stencils, and then spray it one after the other. All right. So our method that we present here, we wanted to have it as applicable as possible, also in an architectural scenario or for an interior design scenario. So we were interested in does it actually work with all materials used in such scenarios? So does it also work, for example, on porous stone, on smooth marble, on transparent PVC, or if you have a sofa, a leather sofa, does it also work on leather? So what we did is we sprayed conductive copper ink on all of these kinds of materials. And we sprayed 20 millimeter long traces in various thicknesses between 2.6 millimeter and 0.8 millimeter. And then we tested if all of them were actually conductive. So, and to illustrate why this is actually a quite challenging task, especially for the porous stone, we see here a zoomed in image of the porous stone. And we see here that this porous stone has really deep cavities. And this is a challenge for all contact-based printing methods or fabrication methods, because for inkjet printing or for screen printing, the stencil that you use here, the net that you use here, has to be in direct contact with the material. So these deep cavities would be really hard to print on. However, with spraying, we create a beam of particles that get pushed into these cavities and then can lead to even a high conductivity in these really challenging materials. So, and that's what we evaluated, and we saw that all of the spray traces were conductive, and even with a fairly high conductivity. So on the y-axis, you see here the average heat resistance, which is expressed here in ohms per square, and you see that all of the tested material have a fairly high conductive, where all of them are below 0.3 ohms per square. So let's look at a couple of application examples. So our first application example is an interactive furniture. So we have here a sofa with a touch button on the back and two proximity sensors on the armrest. The touch button on the back can be used to detect if a person is sitting, and then an app can automatically load a photo album. The two proximity sensors on the armrest can now detect if a person is swiping with their arm to the left or to the right, and then load the next picture or go back to the previous picture, as we can see it right here. And once the user is finished with looking at photos, the system detects if the user gets up and then automatically closes the photo album. Another application example is this interactive music wall. So we sprayed here a music interface on a concrete pillar with a sharp edge. And once the user is touching one of the notes, a song starts. And with this, you can set the music environment in your office space. So the third example is around smart cities. So we sprayed here an electroluminescent touch display on a bollard outside in a humid environment. We coated this user interface with a clear coating to isolate it well from any humidity or from rain, so it's robust to that. And if a tourist comes to this bollard and presses one of the displays, for example, here this monument display, an integrated speaker gives feedback on what kind of interesting sightseeing spots are around and can, for example, give you the history of Bunker Hill. So what kind of limitations and opportunities come with like sprayable user interfaces? So on the one hand, our fabricated stencils are usually 2D, and they are fabricated with materials like cardboard that do not bend around like highly complex geometries. So it would be super interesting if you could also like 3D print stencils that have like a much more complex geometry and could fit to like much more complex objects that we want to augment and that we want to make interactive. A second direction is also how we can integrate more functional materials. So far we focused only on electroluminescent touch displays, but there are also like very interesting other display technologies like electrochromic displays with materials that are very likely to also be sprayable. And third, we are interested in interactive architecture, like in this example here, where an architect implemented like thousands of like gold plates that are controlled with electric motors. So a question is like here on the one hand, with sprayable user interfaces, can we also integrate electronics and just like increase the interaction space by giving more input and output by integrated electronics? And second is also that we fabricated large scale objects that have like a surface area of several square meters, but can we also like really scale this up to like hundreds of square meters of user interfaces? So, all right, to summarize this, we presented here a single layer and a multi-layer fabrication approach that supports the fabrication of input sensors and gives visual output with sprayed electroluminescent touch displays. So since this is, especially as a multi-layer fabrication, a more complex fabrication procedure, we support the designers and makers with a digital design toolkit and a full end-to-end fabrication pipeline that supports makers in their fabrication with stencils. So, and with this, I want to end my talk. Thank you very much for listening to it. If you have any question, please drop me a mail or comment on this video, and have a great day.